Thank you very much for inviting me. It's a pleasure to be back in Santa Barbara. So this morning I want to talk about what we have learned really in the last 5 years about how reionization occurred. And so this is mostly a kind of observational overview, and I'm trying to connect to some of these ideas that we've been learning about yesterday, of how these galaxies in the very early stages of the universe impact their environment. And are impacted by their environment. Just to kind of set the stage, take you back over 13 billion years to the very early stages of our universe. I think for at least those of us who are interested in looking at galaxies, maybe the early universe is kind of a boring place, certainly a very dark place. And it takes a few 100 million years for the first stars and galaxies to form. Oh, in my movie that did not play. Oh, that's sad. Okay, well, there would have been a really beautiful movie from Marcelo Alvarez of, which many of you may have seen, as over the first few 100 million years, the first stars and galaxies start to form in our universe, and ionizing photons emitted by those first stars gradually heat and ionize the hydrogen gas around them, and really fundamentally alter the state of the IGM. And this is kind of, this global interaction of galaxies with their environments on hundreds of megaparsec scales. This process of reionization is really intrinsically linked to the properties of the first galaxies. Oh no, now the movie is going to play. Okay, so this is this process happening, and we think it happens in this kind of bubbly way as it starts in the most overdense regions, these ionizing bubbles growing around the kind of nodes of the cosmic web. And so just to put this into context on our kind of timeline of the universe, what I'm talking about here is this period that we call reionization. We think this is complete, and I'll explain some evidence for that in a moment. We think this was complete within about 1 billion years after the Big Bang, so about redshift of 6. Observationally, it's a really exciting area to probe because this is kind of the frontier of our current observational facilities. So the Hubble Space Telescope, routinely observing galaxies towards the end of reionization, redshift sort of 6 to 8. And now it's exciting to give talks. Now we have JWST. So JWST was really designed to observe the first galaxies in this period during and before reionization occurred. So redshifts up to now sort of maybe 17. We've been observing galaxies with JWST. 21 centimeter experiments like here, and I think we'll hear some more about that today, that will enable us to directly map the neutral hydrogen itself during reionization. So we can kind of get the inside view from the galaxies and the outside view from the neutral hydrogen in the IGM. And so the kind of outline of this talk is I want to argue that, at least for me, some of the questions that I'm interested in understanding by understanding reionization are this kind of question of when and how did the first galaxies form. And I want to argue that we can try and address some of those questions by measuring and understanding the timeline and the morphology of reionization. And I'll explain what I mean by that in a minute. And then during this talk, I'm going to tell you about how we can measure this timeline and eventually the morphology, I hope, using Lyman alpha tomography of the IGM. I'll tell you about how we've been able to measure, put new constraints on the timeline of reionization. And then I'm going to tell you about searching for the kind of earliest starting points of reionization, the sort of nodes of the early cosmic web at redshifts 7 and 8. So yeah, I like to make this analogy that reionization is kind of like baking a loaf of bread. You have these bubbles growing in the IGM, and why does it look like bread and not like a cake? It's the ingredients that you put into it. I maybe don't need to explain this to people who think about the cosmic web. The structure is determined by the sources inside of it. But so what do I mean by timeline? So timeline is kind of like the integrated view of this bubbly loaf of bread. And so here I'm showing you the volume average fraction of neutral hydrogen in the intergalactic medium as a function of redshift. This plot is kind of now maybe 5 years out of date, and I'll show you an updated version a bit later. lots of things going on. The main thing I want you to take away is that the white points here were observational constraints, as I said, a bit out of date, but you can see most of these are just limits. And at the same time, I've plotted these different colored lines, which are different models for how reionization might occur, depending on the properties of early sources, or of the ionizing properties of early galaxies. And so this reionization timeline is really most sensitive to the sort of total integrated emission from the ionizing sources. And so, for example, if you have a universe where you have lots of star formation happening very early, so a very kind of cold dark matter universe, you can form lots of galaxies early. Maybe star formation efficiency is high at high redshift. Reionization can happen very early, and so you'll get models more like this purple line. So reionization starts very early and finishes quite early. But that will be balanced out by, for example, how easily ionizing photons that are produced by the massive stars in these galaxies can actually get out of the interstellar medium into the intergalactic medium to ionize hydrogen. This is something that we call the ionizing photon escape fraction. And if this escape fraction is very low, if it's difficult for ionizing photons to get out into the IGM, then reionization will happen much later, and you'll get models more like the blue one, where reionization kind of pushes to later times. And so there's this kind of, there's a lot of degeneracies, I would say, in this reionization timeline. There are lots of, this kind of balance of how many galaxies are there, how many ionizing photons can get out. But I think I hope maybe convince you just by looking at this plot that it would be useful to constrain this timeline more precisely, so that we can go back to these models and ask, which set of constraints are, which set of physical properties can best explain this reionization timeline. By morphology, I mean, what is the size distribution of ionized bubbles at any given redshift? And so I guess there are really two ways to think about the morphology. So firstly, just the morphology will depend on the average neutral fraction. So a universe that's 50% ionized will have a very different size distribution of ionized bubbles compared to a universe that's 90% ionized. But even at fixed neutral fraction or ionized fraction, there will be we may expect a very different size distribution of ionized bubbles, and that too is very dependent on the properties of ionizing sources. So what I'm showing you here are slices from some simulations by Matt McQuinn, where in each one of these boxes, they were all on average 50% ionized, but you can see that they have very different structures. And this is really dependent on the clustering properties of the dominant sources of reionization. So if you have reionization dominated by low mass, very unbiased low mass galaxies, then you will have this reionization morphology where you have kind of lots of little bubbles, so a kind of more uniform distribution. And by contrast, if reionization is dominated by rarer, more highly clustered sources, so massive galaxies and quasars, well, my pointer is really you'll have a reionization morphology that has these kind of rarer, bigger bubbles. And so we hope that we've been measuring the reionization timeline now. We have not measured this morphology, but the hope is that by being able to measure this morphology, we will learn something about the properties of these very high redshift sources, which I would argue that even with JWST, we won't be able to detect the vast majority of high redshift galaxies. They're just too faint. And so how do we do this? So in the next decade or so, we will have precise 21 centimeter experiments that can really kind of slice up this loaf of bread, and eventually we'll be able to first take power spectrum, but eventually we'll be able to image the neutral hydrogen at early times. But I'm impatient, and it's, I think, really important to have independent cross-checks on 21 centimeter experiments. So this is something that we've been doing now for quite a long time with Lyman alpha tomography. And so this is an approach that's been done with quasars, galaxies, gamma ray bursts. I'm really focusing here on galaxies. So Lyman break galaxies, because they're just really, I mean, they're not really numerous, but they are much more numerous than quasars at high redshift. So obviously, traditionally, Lyman alpha tomography has been done with quasars, but above redshift 7, the number density of quasars is dropping dramatically. I think there's only 2 or 3 quasars known above redshift 7, but maybe there's an update on that. And so, the galaxies are much fainter, but we can do this Lyman alpha tomography in a kind of statistical sense with ensembles. And so the essence of this is that you're just shining a really bright light through your bubbly IgM and observing the imprint of the neutral gas on the spectra of those sources. And so, I think there's kind of 2 key things to take away from 2 important points in Lyman alpha tomography. So Lyman alpha has a very high cross-section for being scattered by neutral hydrogen gas. So it should be an excellent probe of neutral hydrogen. And so this is the scattering cross-section. And so there's kind of 2 features here. So the first is the very strong peak at the resonant wavelength of Lyman alpha. And this is what gives rise to the Gunn-Peterson effect. But you actually, because this cross-section is so high, you actually don't need very much neutral gas to be completely optically thick to the resonant wavelength. So you only need a neutral gas fraction of about 10 to the minus 4 to be optically thick for resonant absorption. But during reionization, what we start to see is the damping wing absorption. So this is due to large amounts of neutral gas at very large scales, so greater than a megaparsec. And so this is then sensitive to neutral gas fractions of sort of 0.1 to or 10% to 100%. So this damping wing effect is what enables us to measure the timeline of reionization. And so essentially what we're doing is looking for galaxies at very high redshifts, so Lyman break galaxies, and trying to detect Lyman alpha emission from them. So Lyman alpha emission is usually the kind of strongest feature in the rest frame UV in star-forming galaxies. It's produced ubiquitously in star-forming galaxies by recombination in the ISM around massive stars. And during reionization, this damping wing effect reduces flux of Lyman alpha. And so what you might observe during the reionization era is something like this, where your Lyman alpha line has been severely attenuated. And so a key observation in the last decade or so has been to follow up large samples of Lyman break galaxies, usually selected from Hubble surveys, follow them up spectroscopically and try to detect Lyman alpha from them. And this is a compilation of some of those surveys. And so this kind of key result we've been finding is that up to about redshift 6, we actually see an increase in the amount of Lyman alpha detected from Lyman break galaxies. That's probably because these galaxies at high redshift, we're seeing galaxies that are less dusty. And so it's easier for Lyman alpha photons to get out. But beyond a redshift of 6, there's a really dramatic drop in the amount of Lyman alpha that we've been detecting from high redshift galaxies. And so this is potentially a kind of smoking gun signature of reionization. We're just seeing much, much less transmission of Lyman alpha from galaxies at this time. I'm going to touch at the end on a couple of peculiar sources, though, that we have been observing at redshift around 8, which have, well, basically no Lyman alpha has been detected in any other galaxies at redshift 8. There are a few sources where we have detected Lyman alpha, and this is potentially telling us something now about where reionization is starting, and I'll come back to that at the end. But how do we connect our Lyman alpha observations to this timeline of reionization, to a measurement of the neutral fraction? So this is something that we've been doing using a Bayesian forward modeling approach. So we want to know what is the neutral fraction given our observations, which are of, for example, Lyman alpha equivalent widths or a flux of Lyman alpha and other properties of the galaxy. And so this is one example Lyman alpha emission line. This is what our data look like. Though I would say most of the time we're actually looking at non-detections. So this is something that we have to fold into this model. And so we can write this as the product of a likelihood times the prior, and the likelihood is something that we then forward model. And due to the very large scales inherent in reionization, this is something that we have to do in a kind of hybrid approach. So I'm not going to go into the details of this, but people feel free to ask me about this. We're taking very large-scale simulations of the IGM. These are semi-numerical simulations, so we can get up to over gigaparsec scale. This is from 21 centimeter fast. And then those IGM simulations are created from a density field, so we can do extended projector, create a halo field, and then populate halos populate halos with empirical galaxy properties. So we can generate, sort of paint on these Lyman alpha and observed galaxy properties, shoot sight lines through our IGM simulations, and generate a forward model of our observations, which we can directly compare to our observations in a Bayesian way to infer the neutral fraction. And so to cut a very long story short, the result is something like this. So this is, I think, now the sort of most up-to-date version of this reionization timeline. And the new points that we've been adding are these orange stars. And you can see there's also several new points now coming from a similar analysis using high redshift quasars, which are the diamonds. And all of these observations are telling a fairly consistent picture that reionization seems to be happening pretty late and potentially fairly rapidly. So most observations point to reionization completing around a redshift of 6, maybe a little bit later, and that there's substantial amounts of neutral gas by a redshift of 8. So what have we learned from this? So again, I don't have time to go into too much detail, but I think this late and rapid reionization is pretty interesting, especially in the context of recent JWST observations. You might have heard that JWST broke cosmology or something, but there has been a large number of galaxy candidates discovered at redshift above, say, 10. And so this is a kind of this is crazy plot, but basically just focus on this kind of shaded area where all of the points which are observations, nearly all of them lie above all of the colored lines, which are theoretical models. So it looks like there is a lot of star formation happening at redshifts greater than 10. I should say these are still all candidates, but it's pretty intriguing. And so one thing I would take away from this is that there are lots of galaxies forming very early, probably, potentially, but reionization happens late. So I think one thing to take away from that is that something is slowing reionization down. And so, you know, for example, this ionizing photon escape fraction that I talked about, it may be that this escape fraction is very, very low. It's very difficult for ionizing photons to get out, and that's one thing that could be slowing reionization down. But I think the next step is really trying to understand how reionization got started and where it got started. And so for that, we're now starting to look at understanding this morphology of reionization. And so we think that reionization should have got started in overdense regions. So these are some bubble size distributions from a work by my PhD student, Ting-Yi Liu. And she's been looking at regions within these large scale IGM simulations at different overdensities. So this is not delta, this is a galaxy overdensity. But you can see the darkest lines are the regions that are very overdense in galaxies compared to the gray line, which is at the mean density. And you can see that the bubble sizes are much, much larger when you look in overdensities. And so that means that we expect to see a very strong increase in, for example, the clustering strength of Lyman alpha emitters. This has not actually yet really been detected, and this is probably because most of the Lyman alpha narrowband surveys are at slightly too low redshift for this effect to be strong. So we expect the Lyman alpha clustering strength to increase when the IGM is more than about 50% neutral. And most of the Lyman alpha surveys are probably a bit lower than that. But we can now start to do this looking at high redshift galaxies. So trying to select Lyman break galaxies that may trace overdensities. And so again, we've been looking in these simulations and finding that galaxies with a UV magnitude of about -22 probably trace the most overdense regions where we expect the first large bubbles to be. And so just throw up a few of these. There's some really interesting regions that have been detected with the Hubble and Spitzer space telescopes. where we've found these very, very luminous galaxies, have later discovered that those galaxies are actually in overdensities, or potential overdensities. So these are just a few maps of these regions, and then subsequently followed those up spectroscopically. And this is where we are finding Lyman alpha at redshifts greater than 7. And so these are some nice examples from JWST as well. So all the red dots, the red stars, are Lyman alpha detected above redshift 7 with JWST. And we're able, with JWST, to spectroscopically confirm these galaxies. Even if they don't have Lyman alpha, we can spectroscopically confirm them now really easily with other emission lines. And so I think these are really exciting regions to start looking at, because the only places really that we're able to detect Lyman alpha now above a redshift of 7 is in these very overdense regions around bright galaxies. So these are potentially the kind of the early nodes of the cosmic web and the starting points of reionization. I would say it's not completely clear, because there are some regions that look overdense and don't have Lyman alpha, but I think this is a really exciting place to start looking. And I'll just leave up, that's tiny areas that we've been observing with HST and JWST, but Roman and Euclid will do this much better, and start to map the IGM on much larger scales. And so in conclusion, I've just told you that the declining transmission of Lyman alpha from high redshift galaxies is implying a fairly late and rapid reionization, and that we're starting to now observe the potential kind of nodes of the cosmic web at redshifts greater than 7, and maybe these are the starting points of reionization. Thank you. I don't think it is.
To turn the switch on. So just a lot of caution, right? So we heard a lot of wonderful results from JWST. Like the first few months, there was this elliptical galaxies at redshift 15 with masses 10 to the 15 or something like this. Right? So they somehow disappeared. So now we hear all these claims about this, a lot of star formation at early redshifts. So it's true that JADES provides a few galaxies at redshift 11 and 13. Problem is that when they model them, right, they find stellar masses and star formation rates that are in above of expectations. Well, if you have a stellar mass and the star formation rate, you can take the first one, divide by the second to get the age, right? And the age is all larger than the age of the universe. So JWST is a wonderful machine, but it still has limited things. So my sort of suggestion, just to wait and make a public claim that all these things will actually go down this time. So this is just all very premature, and claiming that there's something slowing down ionization. It's probably, it may happen, but I don't think we actually have the evidence at this point.
Yeah, no, I completely agree. I think I was maybe speculating there a little bit. I mean, I would say there's two, I'm happy to talk to anyone.
The human tendency is just to push everything to higher and higher redshifts and claim that, all the galaxies form at redshift 10 to the 9 or something.
But I think, I mean, there's two separate issues, and we can talk about this, like the stellar masses, I think, is one issue by itself, like how people have measured potentially very high stellar masses in these potentially high redshift galaxies, and there's a whole, like, a lot of work showing that the stellar masses that you might be measuring can be off by orders of magnitude, depending on the assumptions that you make, for example, about the ages or the prevalence of strong emission lines. But we have observed very bright galaxies, and I think it's hard to get around luminous. Like if something's very luminous, it will be forming lots of stars. But we still haven't spectroscopically confirmed, I think, any of these very luminous galaxies yet. Yeah, but they're not as luminous as, yeah. Yeah. No, exactly. So there, I mean, we know that there are redshift 10 galaxies from JADES, but they're not the luminous ones that are contributing to this. Yeah. Mm-hmm. Mm.
Okay. Okay, just something less speculative about JWST is studying individual galaxies to learn about escape fraction. So I wonder if you can give us your views on where that is and how much it might affect the modeling and so on if we get better real constraints from individual studies.
No, I think that's really important. I don't know if Koki is in here, actually. I can't see him. There's Koki Kaihichi, who was here yesterday, has a program to look at Lyman continuum escape fraction. I mean, I think JWST is not, the wavelength range is such that you can't still directly observe the Lyman continuum because we can only really observe it at optical wavelengths. JWST is observing in the infrared. But I think we can take a lot of the information that we've been learning from, for example, HST, where we can observe the Lyman continuum directly. And there's been, several traces, several other, for example, emission line ratios that seem to trace quite well the Lyman continuum escape, and then try to see how those things change at high redshift. So I think that is definitely a big kind of area that's going to be opening up now. It has. I don't think there's been a few. Actually, there was a paper from GLASS by Sarah Marcia a few months ago where she looked at some of these traces that have been established at low redshift and then looked at redshift 7 and found that I think the escape fractions were, I can't remember off the top of my head, I can look it up, but enough to reionize the universe by redshift 6, basically.
Hi. So you showed us your Bayesian calculation of the reionization history constraint using one 21 centimeter fast simulation, and then you also showed another interesting study of different morphology of the reionization. So I was just curious to know how sensitive is the constraint also to this underlying morphology of the reionization. Are you looking into that?
Yeah, that's a really good question. So that was something that we have looked at. I think at the moment the actual constraint on the neutral fraction is not that sensitive to the reionization morphology. That's probably because we have the redshift range of our observations is fairly broad, and so that kind of washes out information about the scales of the bubbles, the sizes of the bubbles. But I think it's something that we want to do in the future. I mean, my student is working on this at the moment. She was trying to do a Bayesian model comparison, but there's a bug that we have not solved, but trying to see if we can actually start to tell the difference. But I think it's going to be pretty marginal with our current data.
Any questions online? No? Okay. So we have time for one last question and so the next speaker should come and set up.
Hi, thanks for the talk. And I'm sorry if I missed this during your presentation, but did you have any idea if there would be a difference in the morphologies if the ionizing sources were dominantly quasars as opposed to star-forming regions?
That's a good question. I think it would be even more of a kind of biased effect. But I think there's a lot of evidence now that that there just aren't substantial numbers of quasars at these redshifts to do that. But yeah, you might expect to have like these rare, very highly ionized regions if the quasars are dominating.
All right, thank you.
Sorry, hang on, I should get rid of my phone.